Right now, an object older than the Sun is slicing through the solar system. On a one-time flyby, our model said we were unlikely to witness in a single human lifetime. It does not orbit the Sunday. It will never circle back for a second pass. It will flare briefly, shed ancient dust into our sky, and then vanish into the dark between stars, leaving only numbers on hard drives and a hard question: why was something like this here at all? Astronomers label it 3I, only the third confirmed interstellar visitor ever found, racing on a hyperbolic trajectory that guarantees escape, discovered not by a grand flagship observatory, but by an automated survey built for planetary defense. It should have been just another faint dot in a crowded frame. Instead, its orbit solution flashed red. Too fast, too unbound, coming from the wrong part of the sky. For weeks, 3IATLAS hid in the star-cluttered band of the Milky Way, almost canceled out by background noise. Image after image showed only a smudge, barely above the detection limit. Yet when teams stitched those frames together, the path sharpened into a clean, impossible arc, a stranger falling in from interstellar space, cutting across the solar system at an angle that ignored the usual traffic lanes of planets and asteroids. To picture what that means, imagine driving down a quiet street at night and seeing tire tracks from a vehicle that crossed at highway speed, then vanished through the trees. You never saw the car. From the pattern alone, you are asked to deduce the size of the engine, the route, even the distant town it came from. Most people reach for two easy stories. Either 3IATLAS is just another comet and therefore boring, or it must be evidence of something artificial and extraordinary. The reality is more unsettling. Its real importance sits in the space between those extremes in statistics, energy budgets, and the realization that our picture of how many interstellar shards should cross our path may be badly wrong. This channel is inspired by Dr. Michio Kaku's public ideas, but this episode is independently written and hosted. And this is only the first glimpse. In the next parts, the episode will break down how astronomers know 3IATLAS comes from another star, why its path doesn't match expectations, what its light says about the system that built it, and how a single icy fragment can force humanity to redraw its mental map of the Milky Way. The closer we look, the more it stops feeling like a curiosity and starts feeling like a warning from the wider galaxy. Before 3IATLAS could change the story of the solar system, astronomers had to settle one brutal question: was it born here, or was it passing through from somewhere else entirely? The first clue hides in the shape of its path. Most familiar objects, planets, asteroids, regular comets, follow closed ovals called ellipses. Their orbits loop around the Sun, bound by its gravity like marbles rolling inside a bowl. Plot 3. Atlas, and the curve refuses to close. Its orbit is hyperbolic, an open branch that swoops in once and flings back out, never to return. Mathematically, that means its eccentricity is greater than 1, and physically, it means the object carries more energy than something merely trapped by the Sun's pull. Then there is the speed. Even at great distance, 3IATLAS is moving faster than a normal long-period comet that fell from the far-flung Oort cloud. You can think of escape speed as a kind of cosmic speed limit. If an object starts bound to the Sun, its motion must obey that limit all along its path. 3IATLAS ignores it. Run the movie backwards with computer simulations, and it never settles into a distant orbit. Instead, the trajectory just keeps stretching outward, deeper and deeper into interstellar space. Could a violent gravitational slingshot explain it, say, a close pass by Jupiter, or another giant planet that kicked it onto a never-returned track? That possibility was checked almost immediately. When teams rewound the orbit, they found no recent near miss with any massive planet that could deliver the extra boost. The comet arrives already over-energized, as if it were flung outward long ago by a completely different star. The verdict becomes even clearer when you line 3IATLAS up beside its predecessors. 1I Oumuamua, discovered in 2017, and 2I Borisov, found in 2019, both show the same key dynamical signature: unbound, hyperbolic orbits with excess speed that could not be traced to any internal rearrangement of our own solar system. Now a third object joins the list, arriving from yet another direction, like a third strange accent that proves you really are listening to travelers, not locals. The simplest interpretation is also the most radical for our map of the sky. 3IATLAS is not part of the Sun's original debris. It is a fragment from another planetary system, captured only briefly in our field of view as it crosses the inner solar system on its own independent journey around the galaxy. Once you accept that, another question bites harder. If even a modest survey can stumble onto a third interstellar visitor in less than a decade, how many such objects are really out there, quietly threading between stars, unseen, rewriting the statistics behind the scenes? 3IATLAS did not arrive in a vacuum. It is the third act in a story that began with two other interstellar visitors, each so strange that astronomers argued about them for years. Put them in sequence, and you can watch our understanding of the galaxy being forced open one object at a time, like doors in a long corridor. The first was 1I Oumuamua in 2017, a dim, tumbling shard that flashed through the inner solar system before anyone knew to look for it. It showed no obvious coma, no classic tail, yet its path betrayed a tiny push beyond what gravity alone could explain. That combination, no visible jets, but a measurable non-gravitational acceleration, sparked a wave of papers, debates, and headlines about what exactly had just slipped past us and whether we had missed our chance to study something unprecedented. 2 years later came 2I Borisov, discovered by an amateur astronomer scanning the sky from his own observatory. This one looked almost comfortingly normal: a bright coma, a clear tail, behavior straight out of the Comet Handbook. If you ignored its hyperbolic orbit, you might mistake it for a standard visitor from the Oort cloud. Together, Oumuamua and Borisov framed a first contrast: one object oddly quiet, the other intensely active, both undeniably unbound from the Sunday. Now add 3IATLAS. It arrives with its own personality, clearly a comet, shedding dust and gas, yet smaller than many expected for an interstellar object, with activity patterns that do not line up neatly with either of its predecessors. Taken as a trio, these visitors refuse to cluster into a single normal category. Instead, they sketch out a triangle of possibilities, hinting at a whole messy population in between those corners. Statistically, 3 is not a large sample, but when each sample lands in a different corner of parameter space, you are forced to redraw the map. The old picture of rare, occasional interstellar intruders, all broadly similar, begins to crumble. In its place emerges a more chaotic view. Planetary systems across the galaxy constantly eject rubble of many kinds, from bare rocky fragments to volatile rich comets that may spend billions of years wandering between stars, unseen until they cross a survey's field of view. For viewers, this is where 3IATLAS stops being an isolated curiosity and becomes something else. Evidence that our solar system is not a neat, sealed-off family portrait. It is one stop in a galaxy-wide traffic network. And these 3 objects are only the first few headlights we have noticed in the dark, with many more likely still on the way. 3IATLAS is not just unusual because it is unbound. It is unusual because of where it came from on the sky and how it slices through the solar system. Its orbit looks less like a polite visitor merging into traffic and more like a car drifting across multiple lanes at once, cutting against the flow. When astronomers plot its trajectory in 3 dimensions, one detail jumps out immediately. 3IATLAS is on a retrograde path. Most planets and asteroids orbit the Sun in the same direction, tracing out a common sense of rotation inherited from the original protoplanetary disk. Seen from above the solar system, they move counterclockwise. 3IATLAS comes the other way, on a track tilted by roughly 175 degrees relative to the standard orbital direction. It is almost perfectly anti-aligned, threading through the plane of the planets like a needle moving upstream. Then there is its sky background. The Discovery images place it near the crowded band of the Milky Way, where stars are packed so densely that faint moving objects are hard to pick out. Survey telescopes are trained to handle that. Software can subtract static stars, but it is still the worst possible place to try to identify a dim, transient speck. That makes the fact that it was noticed at all feel like a small statistical miracle. The kind astronomers are careful not to rely on too often. Before interstellar objects were actually found, many models assumed that most of them would come from directions related to the Sun's own motion through the galaxy, the so-called solar apex. In that picture, interstellar debris is like dust in a headwind. You expect more particles to come from the direction you are moving toward. 3IATLAS does not neatly line up with that expectation. It appears, instead, from a part of the sky that theory did not highlight as a primary traffic lane. That mismatch forces a choice. Either 3IATLAS is a rare outlier whose odd arrival direction should not weigh too heavily on the statistics, or the underlying picture of interstellar traffic is incomplete. Perhaps the galaxy's debris field is shaped less by one dominant headwind and more by a complex mix of local stellar neighborhoods, past supernovae, and the chaotic ejection histories of many different planetary systems. If that is true, then the discovery of 3IATLAS is not just luck. It is a hint that the real streams of interstellar objects may be flowing through regions of the sky our surveys barely touch, leaving us to wonder how many visitors have already passed through, unnoticed, in the glare of the Milky Way itself. Seen from afar, 3IATLAS could be mistaken for a textbook comet, a bright core wrapped in a hazy envelope and trailed by a faint streak of material peeling away into space. But as the images sharpen and the data stacks up, that familiar shape starts to break into details that don't quite sit comfortably inside the textbook anymore. Hubble and other large telescopes lock onto the comet and track it across the sky, letting the background stars smear into lines. In those frames, 3IATLAS shows a condensed central region, a nucleus buried under gas and dust, surrounded by a soft, asymmetric coma. Models suggest that nucleus is probably only a few kilometers across at most, yet it is shedding enough material to paint a visible cloud across tens of thousands of kilometers. Then there is the tail, or rather, the tails. One stretches roughly away from the Sun, carried by the solar wind and sunlight pressure like smoke blown down wind. But another feature seems to point back toward the Sun itself, an anti-tail that looks wrong at first glance. The explanation is geometric. A sheet of dust left behind along the orbit, lit up from just the right angle, can flip intuition and make debris appear to lean the wrong way. Nothing alien there, just orbital mechanics and perspective playing tricks on the eye. The invisible light tells a different part of the story. X-ray observatories watch 3IATLAS glow where the supersonic solar wind slams into its expanding gas, stripping electrons and triggering high-energy photons. It is the same basic process seen in some solar system comets, but here it carries extra weight. This is the interaction between our stars, wind, and material that formed under a completely different sun in a different corner of the galaxy. Spectroscopy adds another layer. The light from the coma reveals water vapor, simple molecules, and dust consistent with dark carbon-rich material, more like a primitive soot-black asteroid than the bright, reflective comets often showcased in astronomy books. Each piece, taken alone, fits within known physics. Coma, tail, anti-tail, X-rays, organics, all have been seen before. What is new is the combination, an interstellar orbit, a modest but active nucleus, a peculiar tail geometry, and a dark, chemically rich surface, all bundled into a single traveler that should never have come near us in the first place. That combination raises a question that statistics cannot dodge forever. Is 3I/ATLAS a rare oddball, or the first clearly observed member of a hidden class of interstellar comets quietly threading their way between stars? On the surface, 3I/ATLAS is only a single point of data. One more row on a spreadsheet, one more object in a catalog, already crowded with minor planets and comets. But in astronomy, a single data point can function like a fault line. Put it in the wrong place on a chart, and suddenly everything built on the old pattern starts to crack. For years, models of interstellar objects were mostly educated guesses. With no confirmed detections, scientists had to rely on theory. Simulations of young planetary systems flinging out debris, estimates of how often stars pass near each other, and analogies to the population of comets in our own Oort cloud. Those models produce neat curves predictions for how big those objects might be, how bright, how many should cross a volume like the solar system each year. Then the reality check arrived. First, Oumuamua, small, oddly shaped, no obvious coma, and showing a tiny, unexplained push away from the Sunday. Then Borisov, a vigorous, dust-rich comet that behaved almost perfectly like something born in our own planetary suburbs, except for its unbound orbit. Two samples sitting in very different corners of parameter space. Even that was enough to make theorists uneasy about the smoothness of their curves. 3I/ATLAS deepens the discomfort. It is clearly active like Borisov, yet apparently more compact, darker, and on a very different trajectory. In the space of less than a decade, 3 independent detections have filled out 3 different personalities of interstellar visitor, silent shard, classic comet, and modest dusty hybrid. Statistically, that is a warning signal. If the first few objects discovered all land far apart in property space, it suggests the underlying population is broad and messy, not tightly clustered around a single typical type. This matters because those models feed directly into deeper questions. How violently do planetary systems eject debris as they form and reorganize? How many icy bodies roam the galaxy's thin disk at any given time? How often does a random star system like ours get crossed by foreign rubble? Change the answers, and the odds shift for events like cometary impacts, delivery of water and organics, even rare close encounters with massive interstellar bodies. In that sense, 3I/ATLAS is punching above its weight. It is not just an object to be described, it is a constraint to be respected. Whatever story astronomers tell about the galaxy's debris field now has to pass through this point on the chart, and the shape of that story is beginning to look far less tidy than anyone hoped. Once astronomers accepted that 3I/ATLAS was an interstellar visitor, they stopped treating it like a curiosity and started treating it like a deadline. The object would only be bright enough to study for a short slice of its journey. Every night it moved, the geometry changed, and with it, the questions scientists could realistically answer. If they wanted to turn this comet into a moving laboratory, they had to act as if the lab were already rolling out of town. Schedules began to warp around it. Professional observatories shuffled plans, carving out precious blocks of time to stare at what, on most nights, would just look like another small, fuzzy dot. Space telescopes joined in, each from its own vantage point, one in Earth orbit, one near Mars, another out toward the asteroid belt. Together, they gave humanity something it rarely gets with a transient object parallax, depth perception, multiple angles on the same passing fragment of another star's history. From those angles came precision. By measuring 3I, Atlas's position against background stars over and over, teams could pick out tiny deviations from the path predicted by pure gravity. Those deviations, driven by jets of vapor and dust erupting from the nucleus, revealed how the comet was spinning, how fast it was boiling away, even hints about where active patches on its surface might be. It was like reconstructing the layout of a city by watching the pattern of exhaust plumes from planes taking off in the dark. Meanwhile, other instruments peeled back different layers. Infrared detectors read the warmth of the dust, telling astronomers how fine the grains were and how long they could survive in the harsh sunlight. Polarization measurements how the comet's light was subtly twisted, hinted at the shape and composition of particles. X-ray and ultraviolet telescopes mapped the invisible shock front where the solar wind crashed into the expanding cloud of gas, turning the empty space around 3IATLAS into a miniature plasma experiment. The campaign did not belong only to big institutions. Skilled amateurs joined the hunt, stacking long exposures from backyard telescopes, catching faint structures, kinks in the tail, temporary brightenings that large observatories might miss in their carefully scheduled snapshots. For the first time, an interstellar object was being followed, not by a few lucky observers, but by a planet-scale network of eyes and sensors. And yet, for all this coordination, a stubborn set of questions remained just out of reach. Telescopes could tell how 3IATLAS behaved. They could not, from afar, fully decode what it was made of and where exactly in a distant star's nursery its story began. To get closer to that answer, astronomers would have to read the chemistry written in its light. Every time light leaves 3IATLAS, it carries a chemical confession. To extract it, astronomers do something deceptively simple. They split that light apart. Through spectrographs on big telescopes, the comet stops being a fuzzy blur and turns into a barcode, dark and bright lines marking which atoms and molecules are present, how warm the dust is, even how fast gases are escaping. The first thing those barcodes usually reveal in a comet is water. As sunlight warms the nucleus, ice turns directly to gas, and molecules of H2O absorb and emit light at precise wavelengths. Around 3IATLAS, those fingerprints matter more than usual. If its water looks broadly similar to that in solar system comets, it hints at familiar chemistry in a foreign nursery. If its signatures diverge different mixing ratios, different isotopic balances, that's a signpost pointing back to a disk that did not behave quite like ours. Spectra do not stop at water. Carbon dioxide, carbon monoxide, and a zoo of carbon-based molecules leave their own marks. Some cling to dust grains, forming dark, organic-rich coatings that make the nucleus and outflow unusually black to visible light. Others drift freely as gas, tracing out jets and fans, where specific regions on the surface are waking up under the sundae. At the same time, the reflected sunlight bouncing off those grains tells us how rough they are, how large, whether they resemble the fluffy aggregates seen in our comets or something denser and more processed. By comparing 3IATLAS to the best studied comets in the solar system, astronomers can start playing a strange sort of forensic game. If the ratios of key molecules match those found in bodies that form beyond our own giant planets, it strengthens the idea that distant planetary systems may build their outer icy zones in broadly similar ways. If the ratios fall far outside that familiar range, the message is sharper. Planet-forming disks across the galaxy are not all playing by the same chemical rules. That has consequences far beyond comet catalogs. Comets are efficient delivery vehicles. They move water, carbon, and complex molecules from cold storage into warmer environments where chemistry can run faster, sometimes onto the surfaces of young worlds. An interstellar comet like 3IATLAS is proof that such delivery does not have to stop at the edge of a single solar system. Material from one star's nursery can, over immense timescales, drift into the gravitational reach of another. And if fragments from distant systems can wander through our sky, shedding their chemistry into our detectors, then the reverse is also true. Somewhere far away, a different civilization could one day watch the faint coma of a comet and quietly realize that the dust flowing past their telescopes was born in the disk of our own Sunday. Give the universe a mysterious visitor, and the human brain follows a familiar script. It jumps past the slow grind of physics and straight to the most dramatic possibility. Maybe, just maybe, this is not natural at all. Interstellar objects are perfect fuel for that impulse. They appear suddenly, move quickly, and leave forever. There is no chance to send a spacecraft, no way to touch or sample them directly. By the time the public even hears their names, Oumuamua, Borisov, 3I, Atlas, they are already on the way out, trailing question marks behind them. With Oumuamua, the temptation was unusually strong. No visible coma, a tiny but measurable non-gravitational push, an elongation that defied easy description. It was all just odd enough that maybe it's artificial, slipped out of the speculative fringe and into mainstream discussion. That conversation has not entirely gone away. 3IATLAS arrives in that context. The pattern is predictable. A new interstellar visitor appears. Someone notices a strange parameter, its orbit, its tail, its brightness curve, and the word alien starts to orbit social feeds. It is an understandable reaction. The idea that someone else might be sending objects between stars is emotionally simpler than digesting the full chaos of natural processes at galactic scale. But this is exactly where scientific discipline matters. Researchers do not start at the most exciting explanation. They start at the most likely. In practice, that means building a ladder of hypotheses. At the bottom, ordinary common physics. Above that, rare but still natural scenarios. Only at the very top, genuinely exotic ideas. Each new measurement either reinforces the lower rungs or forces you upward. So far, 3IATLAS refuses to climb that ladder. Its orbit is strange but consistent with an unbound comet. Its activity, tails, and X-ray glow fit the behavior of volatile-rich ice under intense sunlight and solar wind. Its deviations from a pure gravitational path can be explained by jets of gas and dust, not by constant controlled thrust. When you line up the data, the natural explanation is not just good, it is sufficient. Yet natural does not mean boring. The deeper lesson of 3IATLAS may be more radical than any single artificial object story. It suggests that the galaxy can, on its own, manufacture a bewildering diversity of interstellar debris and send it drifting between stars for billions of years. No steering, no guidance, just gravity, collisions, and time. If that is what nature produces by default, then the bar for recognizing something truly engineered has to be set very high. The real question, looking ahead, is not, could 3IATLAS be artificial? It is tougher and more demanding. When the next wave of interstellar visitors arrives, what would undeniable artificiality even look like in their light? Centuries from now, historians of astronomy may treat 3IATLAS as a footnote, a small comet that flashed through our sky and moved on. But to people watching in real time, it marks something larger, the moment when interstellar objects stopped being thought experiments and started to feel like a steady part of our environment. Until recently, the solar system was drawn like a bubble, self-contained, its edge fading into the abstract idea of interstellar space. 3IATLAS helps erase that boundary. It is a physical reminder that our planetary system sits inside a much bigger traffic pattern, bathed in a slow, constant drizzle of material flung out from other suns. When we detect one of these travelers, we are not peeking out of our world, we are briefly noticing the world we have always been inside. The timing matters. Over the coming decade, new instruments like the Vera C. Rubin Observatory will scan the sky with a depth and frequency no previous survey could match. Instead of catching one or two interstellar objects in a generation, we may begin to see them as a recurring line item in nightly reports. Each detection will not just be a dot on a plot, it will be another sample from a different planetary history, another shard of a disk we may never see directly. On paper, scientists are already drawing up concept missions. Small, nimble spacecraft sitting in storage or in flexible orbits, ready to launch or divert the moment a new interstellar object is announced. The trajectories are brutal, short warning times, high speeds, huge fuel demands, but not impossible in principle. One successful intercept would turn a passing speck of light into a tangible, analyzable relic from another star's workshop. For now, though, all we have of 3IATLAS is light and time and the choice of how seriously to take what it implies. Ignore it, and the story stays small. A comet with a weird orbit that briefly interested specialists. Pay attention, and the story becomes much larger. A galaxy where planetary systems are porous, where worlds shed fragments into the dark, and where those fragments occasionally cross the gaze of a species just beginning to map its place in that flow. 3IATLAS will leave, and the sky will look unchanged. But the next time a faint smudge appears on a survey image, the question will land differently. Not, what is this doing here? But, how many more of these have we already missed? And what will the next one force us to rethink?